Problem number 18. A cylindrical piece of cork of density rho c, height hc and the cross-sectional area AC is in a larger empty cylindrical container of a cross-sectional area AW. Water of density rho W greater than rho c is slowly poured into the empty container. What is the height of the water in the container when the cork starts to float? Solution for problem number 18. First, let's draw the picture. On the picture we have a container with a piece of cork and water where this piece is just start to float. According to Archimedes' principle, the weight of the water displaced has to equal the weight of the cork for the cork to start floating. If the height of the water in the container is h, then the weight of the displaced water is expression on the left, which is hc/ac, that's volume, multiplied by rho c, which is mass, and multiplied by g. And that's equal to h AC rho W G. After that we can find what is h. So height of the water must be equal to this expression, which is answer B, and that was solution for problem number 18. Problem number 19. A toy elephant is standing on the bottom of a fish tank. The fish tank is filled with water to a depth of 10 centimeters, completely covering the toy. The elephant's legs are perfectly polished, so that there is no water between the bottom of the legs and the tank's floor, and the total area of contact is 0.16 square centimeters. The water has density rho equal 1000 kilograms per cubic meter. The toy has uniform density 2 rho. The atmospheric pressure is 10 power 5 Pascal, and the toy has a total mass 120 gram. What is the total hydrostatic force that the water exerts on the toy? Solution for problem number 19. If the elephant's legs weren't perfectly polished, then the buoyant force would be equal to the weight of the water displaced. Since the elephant's density is twice that as water, the force would be mg/2, which is 0.6 newtons upward. However, since the elephant's legs perfectly contact the floor, they experience no upward hydrostatic pressure. Therefore, we should subtract an upward force F prime equal P plus P atmosphere multiplied by contact area A, which is rho GH plus P atmosphere multiplied by A. Now let's count this. That will be this expression, which is approximately equal 1.6 newtons. And now we can count what is the total force. That will be F minus F prime, which is negative 1 newton. It means that this force is 1 newton down. This is answer A, and that was solution for problem number 19. Problem number 20. A bead is threaded on a frictionless wire and launched horizontally from height h with the speed v0 as shown. If the shape of the wire is a step, as in curve 1, then the normal force from the wire on the bead will point inward. If it is shallow, as in curve 2, then the normal force will point outward. There is exactly one possible shape of wire, shown as a dotted line, for which the normal force of the wire on the bead is always equal to 0. What is the horizontal displacement d of the bead when it travels along this wire? Solution for problem number 20. If the normal force always vanishes, then the bead is only experiencing gravity. In other words, it behaves just like a projectile, and the corresponding shape of the wire is a parabola. The bead travels for distance d equal v0 multiplied by time t, and time t we can find from equation for free fall. That's h equal 1/2 gt squared. From here we can find that time t equal square root from 2g over h, and finally distance d equal v0 multiplied by 2g over h, which is answer B, and that was solution for problem number 20. Problem number 21. A cork floating in a cup filled with viscous fluid is placed in an elevator. Below is a plot of the velocity v of the elevator as a function of time t. Which of the following plots best describes the height h of the cork in the cup as a function of time? Assume that the fluid is viscous enough to dampen all oscillations, that the fluid does not slosh as the elevator accelerates, and that both the cork and the fluid are incompressible. Solution for problem number 21. By Archimedes' principle, the fraction submerged only depends on the ratio of densities between the cork and the fluid, so the answer is E. The statement of Archimedes' principle is that the buoyant force is equal to the weight of the water displaced, and the cork floats when its weight equals the buoyant force. The elevator's acceleration affects the buoyant force and the cork weight equally in the non-internal frame of the elevator. Both forces are weights, so the fraction submerged does not change. That was a solution for problem number 21.